With over 290 million cars on U.S. roads today, it is needless to say that the automobile is a vital part of society. However, as time continues to pass, autonomous vehicle technology grows, which is what our team was assigned to research.
To demonstrate our accrued knowledge and understanding of autonomous vehicles, we were challenged by Professor Lung to perform up to 6 objectives. These objectives are all autonomous goals to be completed using a single executed code, meaning all of them had to be completed after the press of only one button, with no regard for sequence of achievement or the method of how the objective was demonstrated and achieved. We chose to do 3 of the 6 design challenges: kinematics, line following, and sign recognition. We chose these 3 as they all interact well with each other, and additional objectives added an exponentially growing difficulty to our challenge. Going over what each of those terms mean and how we plan to demonstrate our ability to perform these tasks. Kinematics is essentially hard coding to demonstrate that we can calculate the robot's movements and properly program turns and other robot movements. Sign recognition using deep learning is having the robot being able to identify a particular stimulus on the camera and properly respond to that stimulus. Path following using image processing has the robot identify a line and then being able to follow that line. Our robot will demonstrate its ability to perform all 3 of these tasks. With the robot starting at a particular intersection, the robot will execute a hard-coded turn onto a new street via reverse kinematics. After this step is complete, the robot will now be in one of 3 modes based off of what the stimulus the robot interprets from the camera. If the robot sees a stop sign, the robot will stop at the stop sign and then drive past it. Speed limit signs reduce the robot's speed to half its original speed, going off of its base function. And if there is nothing, which is the most frequent case, the robot will utilize its image processing to drive along the road smoothly at a constant speed. Next, there will be a flowchart to better demonstrate the robot's automated process, as well as a more in-depth look into the code and the actual thinking of the robot.
The flowchart goes over the 6 objectives the team covered in labs 1 through 3. The 6 objectives include basic robot control and kinematics, sign recognition using deep learning techniques, path following using image processing techniques, robot network and communication, path planning using MATLAB, and camera calibration position detection using AprilTag. The first process in the flowchart is robot network and communication. First in lab 3, the team had the JetBot send a command to the camera bot to image its current location. And to do this, we linked the IP address of the JetBot and the camera bot in the terminal app. The linked IP addresses, as well as the use of the AprilTag, led to an output of the JetBot knowing where it was on the road. And after this, the team stopped using the camera bot and instead planned a path on MATLAB. The team first converted an image of the road from pixel to real scale, and then we mapped the image in JPEG and set up the JetBot's current pose and goal location to define a path for the JetBot to follow. Next, in Lab 2, the team worked on training a predictive model to classify different road signs. This gave the JetBot the ability to do such things as slow down, speed up, or come to a complete stop when following the path. The team also worked on path planning using image processing. First, the team developed a closed-loop control system for path following. We used a sensor camera measurement to generate heading angles, which acted as an input to the control system. So the input signal passed through the PD controller to generate an actuating signal, and then this signal was then sent to the motor wheels of the JetBot, allowing it to follow a defined path. And using this predictive model to classify the different road signs and the image processing, the JetBot was able to make a decision and continue following the path that it followed. Lastly, in Lab 1, the team estimated the wheel speed of the JetBot by measuring the distance traveled and the time taken to cover this distance. So the main objective of this lab was just to adjust the motor speed and the bias until the JetBot could drive in a straight line. And this kind of familiarized the team with the basic motion and control of the JetBot.
So for this code, in order to understand it more easily, we could break it into 2 different parts: the initializing section and the loop section. So basically, let's start by looking at the initializing section. In here, this is where we have different functions for each different thing that we want the robot to do. So our group decided to do path following and sign recognition. So we're going to have functions for both of these within the initializing part of the code. And so first off, we need to have the camera calibration as a function in the initializing part. And then so this is where we took the yellow and then separated that from the other colors, like we did in Lab 2. And then from there, we were able to calculate the heading angle, and then that's all applied to the path following. So that's all going to be functions within the initializing part of the code. And then the last part would be the sign recognition. And that's going to be a separate function in the initializing part of the code. And then so this is where we can assign different numbers based on the trained model that we created in Lab 2. So if the robot detects nothing, we can assign that to a 0, and if it detects a stop sign, that'll be a 1, and if it detects a speeding sign, that would be a 2. And then so these are all different functions within the initializing section, and then now we can jump over to the loop where the code would actually be run for the robot, really. And so in the loop, one frame of the one camera frame equals one loop. And so basically it starts off by activating the camera. So the camera is going to capture a frame. And then with that one frame, it's going to run through a bunch of different if statements. So, and each if statement is assigned to each different sign recognition characteristic. So like a 0, 1, or 2. And so basically if the sign recognition detects a 0, then it's going to run through path following, and it's going to keep on path following through every frame that it detects 0. And then so eventually the robot's going to come up to a stop sign where it's going to detect a 1, and then it's going to run through the if statement for the stop sign, which is the robot's going to stop, and then it's going to move forward until it is past that stop sign, and then it's going to go back to a 0 where it's going to continue along with path following, and then the robot might come across a speed sign, and then it's going to detect a 2. And then at the speed sign, we have our robot programmed so it speeds up slightly at the speeding sign. And then after it goes past the speed sign, it's going to just detect an empty road again, and then it's going to do path following. So that's basically how we put together the path following and the sign recognition for our robot.
Through our research and time spent during the labs, our team was able to accomplish our 3 objectives with our robot. Additionally, through our labs and by completing this project, our team gained insight into how autonomous vehicles have the potential to change the future of the automotive industry and the world.